See you later, guys.
Okay. Hello, everyone. So basically, while Stefano prepares and does the last tuning for the thing that you see here, I will basically cover what we are going to do with this experiment. Okay, so we are going to create a supermassive black hole that will swallow the villa completely into oblivion. No, I'm joking. The only supermassive black hole for now has been in our finances to buy all this equipment. Let me tell you briefly what this does. Okay, does this work? No, no problem. Jesus. Give me a second. I'm very sorry. Okay. So yeah, so today we are basically going to showcase how standard quantum key distribution infrastructure can be used to make trusted execution enclaves more secure. So what this means is that in particular we will implement one-time programs using TEs and conjugate coding. Now, there are a lot of mysterious words in this slide, so we'll start with a recap telling you what this is all about. So a Trusted Execution Enclave, or in short, TE, is a chip that has an hardware module in it that is secure. So basically, there is some part of this chip that has some cryptographic keys burned into it that cannot get out of it, and because they are very difficult to extract. You literally need an electron microscope to do that. An example of this is your hardware wallet, if you have one. Basically, there are some private keys in it. You access them by specifying the seed phrase, but they never come out of your wallet. You just pass a transaction to the wallet, it gets signed, and it gets out. So you can pass encrypted information to the TE that can be only decrypted on the chip. And this allows you to do a lot of cryptographically strong things. So, okay, so one of the things that you can do is one-time programs. Okay, so one-time programs are basically programs that can be executed only one time. They are useful for a lot of financial and blockchain applications. Now, there is a theorem that basically tells you how one-time programs are provably impossible to realize, both classically and in the quantum world. To do this, basically, you require some sort of trusted setup to build a one-time program. It's not something that you can just build out of standard cryptography. TEs offer one option for this setup. So basically, if you have a TE, you can do a one-time program with it. And the idea is that you encrypt this program, you send it to the TE using the TE key to encrypt it that you don't have access to. You only see the public key of this thing. Basically, the TE executes this program, and then it locks itself, and basically say, okay, now I cannot do anything more. Now, obviously, this makes the program not executable twice, but has some downsides. Most importantly, when you do one-time programs like this, the word you should focus on is lock. What does it mean that the TE locks? Well, obviously, I could implement literally a hardware switch to do this, but I don't want to throw a TE out of the window every time I need to run a program. But if I don't throw the TE away and then I need to, make it reusable, I could basically try to find some hacky way to some loophole in the TE logic so that I can execute the program more than once. These things are called replay attacks. They've been demonstrated and they exist. So what we want to do with this weird setup is leverage quantum physics to make this impossible or like incredibly hard. So now let me give you an introduction to quantum. So first of all, what we are doing here is an experiment in quantum information. Now, quantum information is a radically different thing compared to classical information. So the main difference that you have to keep in mind is that a classical piece of information can be copied at will. So for instance, if I tell you in 40 minutes we'll have lunch. You can literally take this information and tell it to everyone you know, and they will know. You can copy this information at will. Or files, you can copy-paste files. Quantum information instead behaves like a resource. It's not something that you can copy. You can transfer it around, but you cannot copy it. This is called no cloning theorem, and is one of the most important theorems, basic theorems of quantum theory. So this simple idea is the basis of quantum cryptography. Now, let me cover the basic unit of information that we will use in this experiment. So you probably heard already the word qubit. A qubit is the main computation unit of quantum computing. So probably you know what a bit is. A bit is something that is either 0 or 1. A qubit instead can be any point on that sphere, which is called the block sphere. So you can see that it's not just like two things. It's a continuum of things, an entire surfaces of possible states. Now, the most important thing is that if I give you a qubit, in principle, you do not know which point in this sphere the qubit is. So we know that it's here now, but if I just give you a qubit, you need to measure it to see what state you have. We'll get to measurement in a second. What you can do, though, is you can transform this qubit. So you can basically rotate this sphere, and the qubit, can change place. But it's a kind of a blind operation. Like I have an operation that says rotate whatever thing I have 90 degrees along this axis. Whatever I have will rotate 90 degrees, but I didn't know what I had before. I don't know what I have now. Because I'm like performing this operation like I were blind. Now, to access the information, you need to measure the qubit. What does it mean to measure a qubit? It means that basically you choose an axis on this sphere. In this case, we are choosing this axis that is conventionally called the z-axis, 0, 0, 1. That's just standard quantum nomenclature. And when you measure, what happens is that this point that you had collapses either to 0 or to 1. So this qubit gets destroyed in the process of measurement and becomes one of these poles, becomes either 0 or 1. Now, how does it happen? This is a probabilistic process, basically. There is a probability that it will become 0 and a probability that it will become 1. Now you see that the more this thing is close to one of the two poles, the more it's likely that it will end up being there. So for instance, this thing is way closer to 0 than to 1. So when we measure it, like probably 85% of the times we'll get 0. If we had this qubit, like 1,000 of these qubits, I don't know, 850 times we would get 0, and the rest, 150 times we would get 1. Now, importantly, notice the following thing. If I have this qubit here, so I have a qubit in the 0 state, if I measure along this axis, I will always obtain 0 because it's literally coinciding with 0. So in this case, the probability of this thing being measured becoming 1 is 0. The probability of being 0 is 1 because basically it already coincides with the axis I want to measure on. But if I measure along this axis, you see that this thing is completely unbiased. It's like it lies like that, and it could go one way or the other with equal probabilities. So I can go either to this thing here that we call conventionally plus, or this thing here that we call conventionally minus. Now the important thing is that this thing that I had before again gets completely changed in the measuring process. So I basically lose this information forever. And if you think about it, I'm transforming this thing into pure noise. I'm saying I have a thing here, now I flip a coin, and I will get one of these two things here. This is also true vice versa, obviously. So if I have like something like this thing here and I measure it along this axis, it's the same. I'm basically destroying that information and going up or down with equal probability. Okay, so this is the basis of something called conjugate coding, which is what we are doing there. So the idea of conjugate coding is the following. imagine that I have two bits, two classical bits, and I want to encode them using a quantum computer in a way so that I can recover only one of these two. So you want to choose, okay, I want to recover the first or the second, and when you do, the other one is permanently destroyed. How do you do it? Well, you encode the first bit as a qubit in this axis. So if your first bit was, say, 0, you instantiate a qubit in this way. If it was 1, you instantiate it in this way. For the second bit, you do the same, but on this axis here. So if you had a 0, you encode it as plus, and if you had a 1, you encode it as minus. So these are called Z and X bases conventionally. Now the point is that you have two qubits, and now these two qubits represent your classical bits. You have encoded a classical bit into a qubit. Now you scramble them, like, you just permute them, and you don't tell your friends which one encoded which bit. So now they see two things. Remember that you cannot access that information without measuring. And now what they say is, okay, I wanted to recover the first bit. Well, if they want to recover the first bit, they know that it's encoded in this axis. They just don't know which of the qubits it is. So they will be forced to measure both of the qubits in this axis here, and in the process, they will completely destroy the information about the other qubit, which was encoded in this other axis. So this is the basis of the thing, and what they will get was the original bit that they wanted to access, plus some noise, some random noise. Now, they will basically need the TE to distinguish between which is the noise and which was the bit. So the TE will have the information inside. It will say, yeah, I know that, the first bit was encoded in the second qubit, for instance. So you do the measurements, you give the measurements to the TE, and the TE can say, okay, yeah, you measured in this order, I know which is which, so now I can tell you which one is noise and which one is the thing that you wanted. So how do we use this to do, why do you need that weird stuff there? The reason why we need this weird stuff there is that the way we implement this is with this kind of infrastructure. We have a laser. One party that we call conventionally Alice has a laser. This laser shoots single photons. And the other part is Bob that has a detector, so has a thing to detect these photons. Now, what Alice does is she polarizes their photon. Polarization is a property of light. You apply a filter and you can polarize vertically, horizontally, diagonally. You have various choices. So now what Alice does is, you can see here, if she wants to send the first bit and the first bit is 0, she polarizes this way. If she wants to send the first bit and it's 1, then she polarizes in this other way. And she can use oblique polarization for the other bases. And now what Bob needs to do, Bob needs to measure the polarization of this photon. And it sets the detector by putting a filter, a screen. And basically you can see that, if the detector is the wrong one, it will measure in the wrong axis. So this is just like the practical implementation of the thing we were talking about. Now, what we did code-wise is coding something called Trust that basically uses all this bullshit that I told you about to create one-time programs. So it's a small library to do conjugate coding-based one-time programs on TEs. It's written in Rust, as the name can suggest, and can be used in embedded systems. So it can be run on very small chips. That's the repo on GitHub. If you want to play with it, is MIT licensed, is completely free, so feel free to explore. So how does this work? The protocol is basically run in 3 phases. In the preparation phase, you basically are the preparing party, Alice. You prepare the qubit, and you send them to the measuring party using QKD infrastructure. So basically, you have the laser, you prepare the polarization, and you send it using fiber optic. That thing here, that big red box, is the laser. Those things, small things here are... Yes, I'm pointing lasers at the lasers. The small things are detectors. So in the measurement phase, you have... together, sorry, with this information, she also sends her encrypted one-time program to the TE, which is owned by Bob. Now Bob says, okay, I want to run my program. So what do? Well, I choose an input to evaluate the program on, and the TE tells Bob which choices of measurement he has to operate. At this point, the TE receives the measurement outcomes and decides to run the program or not, depending on, whatever inputs were received. So in practice, the way this works is like this. Inside Trust, there is literally nothing more than an incomplete table. So we have some entries. As you can see, some of these entries are filled, some are not. The ones that are not filled are marked with zeros by another row called bitmask, and the ones that are present are marked with 1. Now, the difference is that we call these 1 entries here security bits. These are the secret bits because not even the TE knows them. So what happens is that also the TE stores the information about the orderings. So for instance, it knows that this represents basically the first bit string that we want to send. So as I told you before, I want to send 2 bits so that only 1 is recovered. I'm doing this n times, so I want to send n bits so that 2n bits so that only n gets recovered. So this is the 0 bits, the first bits in our initial examples. These are the second bits. And the ordering thing is telling to the TE which qubit will encode which bit. So in here, we know that the first qubit encodes the first bit, the second qubit encodes the second bit. In this case, it's the opposite. Huh? Oh, yeah. Andrea, can you find some black tape somewhere, some gaffa? Thanks. Okay, so this is how we implement this in code. It's basically just a struct. Now, what happens is that during the measurement phase, the TE operator will basically choose an input to evaluate the one-time program on. What we do now is we compute the hash of this input. Hash is a cryptographic operation which is quantum secure. And what it gives you is you take the input and you get a string of fixed length of zeros and one. Then basically this string will tell the TE which measurements we have to operate. Pictorially, it looks like this. Basically, this is the hash. This thing here, choices, are the hash bits. And they will basically tell the TE, you here want to measure this bit here, here you want to measure this bit here, and so and so. Then you do the measurements, so you measure all these couples of qubits that you have, and you will obtain a string of outcomes, like so. Now what you do is, when you have, the 0 entries, you don't write anything here. Wait, okay, this is what happens right now. So you have this string of outcomes, you have the orderings, you have the choices, etc. Now, what you do in the result phase is that the TE takes the measurement information, takes the preparation information, and decides if it wants to run the program or not. How does it work? Well, it basically uses the ordering information and the choices information to decide for each couple which one is noise and which one is not. This is written in the purged row. So for instance, you see in here, basically, the first, this bit was encoded by the first qubit, but I wanted to measure. And we are on again. Okay, so what happens is that, for instance, in this case, I wanted to measure the first qubit, the first bit, which was encoded in the first qubit, in the second qubit, which is this one. And so this is what I have here, and this thing I forget. So now I report this information here in these small triangles, the outcomes of the measurements. And now you can see that this is, in this case, you know, for the security bit, what I had before, this is what I measured, and these two things have to coincide. So for instance, in here, they do not coincide, which means that the measurement didn't give me what I wanted. So this could either mean that there is noise or there is tampering. In any case, what happens is that if I do not trip a huge number of security bits, the TE will use this to give me a secret string. So basically, in the secret bits that are, you know, the ones with the 0 here, it will take this number and it will spit it out. So this goes here, this goes here, this goes here, this goes here, this goes here. Basically, okay, perfect. So that's what we do. And the point is that now we can use this secret to either run a one-time program directly on the TE, or to feed it to something else like a garbled circuit to evaluate a one-time program in an even more secure way, but I won't talk about it right now. So as I said, basically there are two ways of using these things. The one is the pure TE modes. In this case, all bits are security bits. So in this table here, there will be basically no ones. They will all be, sorry, no zeros. They will all be ones. And again, I can use this as a test. If I pass enough tests, I run the program or not. The upside of this thing is that it gives better protection against replaying than standard TEs, and it's fully stateless. The downside is that if the TE is hacked, we are game over anyway. The second way to do this is by having the secret bits, and again, these secret bits can be used to unlock some other cryptographic protocol, such garbled circuit. The upside is that at this point, if someone steals the root of trust, we do not care too much. Like the TE becomes really hardened, and the reason is that basically, if you see in this example here, the security bits were not in the TE in the first place. So even if someone hacks the TE and reads the information before the measurement is done or after the measurement is done, they cannot extract this secret string. To extract this secret string, they should be very strategic, hack the TE only when the measurement happens, hack the code inside so that the measurement is strategically done in a weird way, and then basically they could access the full secret. But the point is that if you hack this thing right now, you just get out something that is what you wanted in the first place. This won't allow you to run more than once your program. And the way this is used is that then you feed this to a garbled circuit or other primitives and you do it. The downside is that this is computationally slower. Okay, so feel free to play with this stuff. We provide plenty of examples. This code can be run on this chip here, which is only $4. So if you don't have, you know, the remaining $100,000 that are in that box, but you still want a hint of how this thing works, we also offer a simulator, which is basically a classical program that simulates the output of the QKD-based measurements. Obviously, these will not be secure, but it will give you a feeling of how this stuff works. And yeah, now we go to the demonstration, basically. I'm done with the presentation, so with these last 20 minutes, I think we can go. Are you ready, or not really ready? We'll see. So, okay, let me also cover very shortly why we have a box or stuff like that. So, as I told you in the beginning, basically the way, Jesus Christ, sorry. Basically, the way this thing works is by shooting photons. You see here, we were shooting photons. Now, unfortunately, all around us, we are surrounded by, guess what, photons. So we need that black box to shield the lasers and the detectors from the ambient light interference. That's why it's completely covered. But yeah, so inside there, what we have is the laser, which will shoot this thing, these photons that will be split and then measured. You know, in the full, like, real example, as you can say, as you can see here, Alice and Bob should be spatially separated. So there should be some, for instance, kilometers of fiber between these two parties. Obviously, here we are doing everything in a self-contained way. So it's all here. By the way, let me tape the thing. We have the gaffa, so can I tape it or? Yes. No, you don't have to close the windows because we have the best invention of humankind, which is duct tape. So the funny thing is that both me and Stefano were basically theoretical scientists. So, when we bought this thing in the first place a few months ago, we were like, oh, what the fuck? What we did for 10 years is actually doable. Stai facendo la signature? No. Che vuol dire lo lasci? Dammela, mandamelo su. Mandamelo su WhatsApp. Mandamelo su, vai. Grazie. Grazie. Okay. So now let me see if my computer can be plugged into this thing. I'm very skeptical because I use a weird operating system, but you can never tell. Give me a second. Can I also plug mine? Yeah, but I wanted to show. If it works, I'll eat my boots, literally. Yeah, so we have a little helper which is basically formatting an Ethereum transaction right now. And as you know, in blockchain, what you do is you sign the transaction. Signing a transaction literally means signing the hash of the transaction. So, exactly. Yeah. That thing there? Do not take this one because if you can go to transaction helper and no, I know, just show the code. Transaction util, transaction preparer, yes. Perfect. All right. So in here, basically, what you have is, you see, we have from address, that's a sender, to address, we are sending to the 0 address, the value, which in this case is 1 ether, and then we are basically formatting this transaction. Now, Stefano cannot run this thing because Ethers RS doesn't build on his system, unfortunately, but what this thing spits out is the transaction hash that needs to be signed. Now, I will basically give this hash to him so that he can pass it to the TE, which has a secret key burned into it, and then we will get the signature out from the TE. I'm literally passing this thing on WhatsApp, so. WhatsApp? Yes. It's very artisanal, as you can see. Can you send it on Telegram by any chance? Yes.
Yeah, Telegram. I think Telegram works better.
Okay. So I'm copying the hash and I'm pasting. So okay, I paste the hash on Telegram. It's that one. Just yeah, copied. Perfect.
Okay, so I'm gonna keep it here for safety.
Yes.
All right. So these are the two windows that I will use to pass. Maybe a brief. Can I have a minute to say what's in the box?
Yeah, I also passing you the raw transaction, which is not signed. So if you put this on Etherscan, it will show you that it's a transaction, it's valid, but it's not signed. There is no signature, and so it cannot be executed.
Why not?
Because it has no signature, right? So
All
if you do, if you if you go on Etherscan and raw transaction signer. Wait, I'll send you the.
It's fine. I'm sure I can find it. This one?
Transaction, broadcast, maybe.
This one?
Broadcast raw transaction. Yes.
Yeah.
If you copy paste that string and you. What is this?
No, this is signed transaction.
Wait a second. Decode.
Well, I just start by getting the signed transaction first, and then we can.
Yes. Okay.
Yeah. All right. So, couple of things. Just for you to know what's effectively in the box. And this.
I have the thing, by the way. This one.
You have the what?
Yeah, yeah.
Okay. That's a very interesting address.
Yeah, so if you copy paste that thing in the raw transaction X and you decode,
yeah,
you can see that there is no why there is a signature? Yeah, okay, there shouldn't be a signature there. I think that's randomly calculated. So,
it's okay.
Going.
I will just do other things in the meantime. There's plenty of things to do anyway. So here is the brief, very brief explanation of what's going on here. Got it. So that's all we needed for this demonstration. That's the packaged contents of this box as they were in London just before I put them in the hands of some trusted couriers that brought it here safely. It turns out, quite incredibly. I didn't imagine that. That's almost all we needed. What we really needed for this particular project was a skilled watchmaker who spent about a month of time going from theoretical quantum information person doing quantum gravity for his PhD to learning how to do experimental quantum photonics, because apparently that's what his job is right now. So that's the necessary components for this experiment, including personnel. He taught me how to do it yesterday, but I wouldn't have been able to do it without instructions, honestly. These are the individual pieces. There's a photon pair source, which is a big laser. In fact, it's a small laser, but it has a big pump laser, and then there's a lot of loss. And a few photons, very sparse number of photons, come out of 2 fiber optic cables from the front. In fact, they are so few that we have to tape the box down and tape it at the bottom, because just the sunlight that comes through that little aperture in the front is enough to drown the signal from that and make it hard for me to run the experiment. The noise threshold goes high. So that's the generator of the photons that get into the experiment. And then there's the end of the photons. That's where the photons start their, so here the photons start their life. Here a brief few nanoseconds after, in fact, I think picoseconds after, the photons end their life. They slammed against the detectors, and the detectors emit some signal which we can record on some microcontrollers and use to determine whether we have seen the 0 outcome, the 1 outcome, or we just missed the photo. And for your information, that's what the signals look like on an oscilloscope in our London office. These are just 2 of the photons, so the 2 photons that come out. and they come out, typically they should come out perfectly aligned of the laser, but because there's always photons drifting around, no matter how well we tape that, there's a bunch of other signals. It's just that they are not perfectly aligned. They have to be timed exactly for the detector to look at it. Except the timing difference between them, you can't really see it here, but I can tell you the spacing is in the order of a few hundred nanoseconds between different pulses. The spacing between the photons is tens of nanoseconds, sometimes single nanoseconds. And so you need to have something which has that precision to detect which ones are actually the coincident, the correlated pairs coming from the laser, which is the signal for the protocol, and which ones are just random photons that come from the air and enter the box, and you don't want them because they carry who knows what information. And what you need to do is you implement a small piece of electronic circuitry, which is called a coincidence detection. And what it does is when the signals are sufficiently aligned, there's a bunch of MOSFETs and resistors that implement effectively an AND gate, but a very short-term one. And they translate these very short peaks, which by the way would be too short for the microcontroller to reliably detect anyway. And they translate them into a pulse that is longer, but only comes if they are sufficiently well timed. If they differ by even like 20 nanoseconds, the pulse doesn't come. It just gets lower very quickly. And so this allows us in hardware to detect coincidences before we pass them to the microcontroller. So one of the photons that comes out of the laser is entirely wasted. It's only used for this timing purpose. And it tells you when to expect something in the other detector. What is noise and what is not noise. Without that photon, you do not know which photons are the interesting ones and which photons are just random from the air. In fact, there's many more random photons from the air than interesting ones, and this is a cryptographic impact because it allows you to hide some of the error. Even if you have a bit of error in your protocol, as long as there's enough thermal photons from the air, from the light, then those will drown whatever imperfections in your signal. You know, because you can do the coincidence detection, which ones are the right ones, but without the herald photon, you can't do it. Other pieces, practical pieces that the photons go through, there's a beam splitter. The beam splitter is a way to take a photon coming from one path. So you use effectively, we decided to use an encoding of qubits, which is called path encoding. We use the 2 fiber optic cables for each photon. And depending on whether the photon is in the first cable or in the second cable, the bit encoded is 0 or 1. And this is very classical. It's just classical light. But because photons are quantum, what you can do is you can pass them through a reflective cube, which there's like a laser, a test laser coming through. This one is invisible. And in this cube, photons enter from one port, and they get split on both paths at the same time, with a phase in between. So now the photon classically is on both paths in superposition, and the phase between the paths is the thing that encodes the bit. So if you try to measure the 2 fiber optics, you plug them into the detector without doing the correct measurement, you just get 50-50 random coin flips. Nothing interesting. If you want to decode them, you pass them through a second one of these, which scrambles them and makes them come out of the correct port again. So this is a way to pick the basis that you want to encode information into and decode information from. Then you have some switches, which are used to communicate classical choices to the photons. It is very hard. I mean, photons travel really fast, the speed of light, which is fast. You cannot really time operations mechanically that fast, and nothing complicated. So the best way to work with photons and implement quantum computations is to have fixed sets of equipment that do different things, and have one kind of component that is fast, which is a switch. And the switch, all the switch does is decide path 1, path 2, nothing else. And you have a bunch of these switches together, and you can use one to decide which basis, one to decide which bit to encode, then they go through 4 different paths, then they get merged together, and they get sent to the destination. The destination does the same thing. It has 2 switches that decide which basis to measure in, they go through 2 different paths, merge again, and get detected. And so you have all of these paths that are alternatives. The photon is only in one of them or in 2 of them in superposition or in many of them in superposition, but they need to be merged back into one, and that's what fiber mergers are for. We only need 2-to-1 fiber mergers. So 2 fibers come in, it's fused fiber optic, it's a very precise process. The photons come into this junction and they come out of a single fiber. And this is a polarization, all of this is polarization maintaining because we use polarization for part of the process. And finally, we have the stars of the show, which are the microcontrollers. There are two of them. One of them controls the encoding side of things. One of them controls the decoding side of things. In reality, they would be in different places.
Alice and Bob, yes.
Alice and Bob. But in here, because we need to do a compact demonstration, they're in the same box. One of them decides which basis to encode the secret information into and which bit to encode, and the other one decides which basis to measure the information from. And so they are attached to the various switches that we have that control the paths of the photons. That's the way this experiment runs. Laser is on, box is sealed. Hopefully there's not a lot of interference in there right now. So I'm going to start running things.
So if you go on Telegram, you can see I sent you the right RPC at the moment.
Okie dokie.
Okay.
I am, yeah, give me a second. I will go on Telegram. Yep.
So you can see it's considerably shorter because it's actually not signed.
Yep. So this is the one.
Yes.
And I'm going to
if you paste it there, yes.
Yep.
The code, you will see that there is basically no signature information. It should come right after value. It does not because there isn't.
It does say valid false.
Yes, because it's not signed. Cool. So I also passed you the hash, and then you can put it.
Yeah, so first things first, there is a bit of the protocol that involves the secret that these two enclaves should have. The information in this secret is a couple of tables of bits that need to be produced. There's 2 rows in this table, and we need to pick the ordering of the bits in the table, so whether 0 means X or 0 means Z. This is the secret information that's shared by the 2 TEs. We put it as the first input of our program. So let me flash the 2 chips and run the programs. So first things first, I'm gonna flash. Program 1 goes on COM4. That's the one. It's waiting for the hex string from the serialization utility. Program 2 goes on COM6. I had to write them on my arm to remember. And that's also waiting for the same information. So this is the secret table that the 2 TEs would have stored inside and would use to decide how to encode the data and how to decode the data. So this information comes from a small utility that we have, that Fabrizio has written. I shall not take credit for this. I'm gonna just put 2 security bytes because it's a short demonstration. So let's say 0x0123, 0x4567, and 0x89AB. And this gives me, there are 16 bits here, 16 bits here, 16 bits here. There's 48 bits. They get encrypted using the TE key. So technically, you'd give this information. This information can't be read from the outside. It's decrypted by the enclave. So you can pass this, but only the enclave knows what the table is. So this is encrypted with a key that's secret to the enclave. Use it as you see fit, and I shall see fit to use it here. So enter it on the controller, on the sending party, so Alice. Enter it on the receiving party, say Bob. And now I am told, okay, this is valid information. Please provide the input to your program. The input to my program is going to be the hash to sign.
No, not that one. If you go on Telegram, this is the raw transaction. Yes, that one.
This one?
7cc.
7cc.
Yep.
And so this is the hash of the transaction, which I will put here.
Yeah.
And if everything goes well, which it never does, well, no, not error. The watchdog has killed the program. Let's try again. These things are as fiddly as they can possibly be. But this time I will be fast. Done.
Yeah.
Bunch of bits were generated. for debugging purposes, I have printed them. You wouldn't. This is the secret information. See, the information I sent initially has, let me just kill them so that the watchdog doesn't restart them. The information that I sent, this was secret information that was decoded by the TE internally, and it contained these secret basis choices, these secret bits for the Z basis, these secret bits for the X basis. And these were used to generate a bunch of switch inputs that determine whether the photons went into the X path or the Z path, whether the bit encoded was the 0 bit or the 1 bit. And on the other side, the detector received these photons, looked at the detectors, got some bits out of the detection process, and these were the bits that were obtained. Sorry, these were the bits that were obtained. These would be the measurement outcomes. They were validated, they were valid, and the security was verified. This was a fairly well-tuned procedure, and it worked out for this program execution. So now the TE internally has a key. The key was used to sign this transaction, and now this information that I have should be the one that I paste, right? If I've done everything right, which I am not sure I've done, how do I verify it?
Yeah, let's see. I think you should give it to me so that I can give you the RPC, because that's a signature.
Yeah, but can I not verify the signature by myself in some?
I don't know. Yeah,
no?
try.
Enter a sign.
I don't know if try. I don't know if the format is.
No,
is
fair
the
enough.
right
So
one,
I'll just send it to you.
just send me the transaction.
Yeah.
Now, what I would like to show you my screen, but it's a nightmare. We do computers at the same time. Yes. So. Second. Now, basically, I will copy this signature into my program.
You want the cable?
No.
I mean, I'm done.
No, the problem is not the cable. The problem is my computer. Okay. Cargo run release. Okay. Now I should have this thing, which is, I post it here. Okay. Now if you go with this one.
I do what?
Just copy it in the transaction decoder.
Yeah. This one?
Yeah.
Yeah. And
now, if you go to the code, you will see it's all the same, but now there are 3 more parameters, V, R, S. Those are the signature parameters. So now the transaction is signed, and indeed it says valid true, because the transaction now can be executed. So,
yes.
And the important thing is that all the signing happened on the TE. So, you know, in a real case scenario, only Alice has the private key, sends it to the TE, and Bob basically gives the transaction. It works like another wallet, basically. Bob takes the transaction, feeds it to the TE, and the TE signs it for him, and then he broadcasts it, with the difference that he can sign any transaction he wants with that secret key only once. Then he cannot do it anymore because he destroyed the quantum information encoding the table in the process. And that's it. Yeah. Thank you.
Thank you very much.
If you